So I wish to welcome you all to this new series of colloquia of the Italian Society of Statistical Physics. It is with a lot of pleasure, great pleasure, that we have with us today Marc Mézard. Marc Mézard doesn't need many presentation in our community. He is an extremely well-known French physicist who in recent years has taken the decision to move to Italy and continue his scientific career in Italy, in Milan, at the Bocconi University. As the Italian Physical Society, Statistical Physical Society, we are extremely proud and happy to welcome Marc in our community, and we are very thankful, and we hope that in time you will have the opportunity to know the different groups that are active in Italy scientifically, and to interact more and more with the society. So we really look forward this talk that is has a very appealing title, very intriguing, and this talk will be in a hybrid format. So I wish to thank the Dipartimento of Scienze Matematiche, Fisiche e Informatiche in Parma, who has given us the possibility to hold in hybrid format this colloquium. In particular, I would like to thank Raffaella Burioni, who is always extremely available toward the society. So thank you, Marc, again. Looking forward to our further interaction in the future. And I leave the floor to Raffaella, who will introduce the speaker. Thank you, Marc.
So I just wanted to give a few ideas and a little bit of a historical background, let's say, on what is taking place now, what is happening, and that we all know. But it's important to remember that what we are witnessing live, an industrial and technology revolution, which is of unprecedented dimension, which is the AI revolution. It's based on neural networks. It's okay? Yeah. It's based on neural networks, and the real revolution, the recent modern AI revolution, it starts at a very well defined moment, which is 2012. 2012 is when the first time there is a neural network model, AlexNet, which wins a competition to classify images. And so it's the beginning of really the analysis of images done by neural networks much better than any other program. And I like to start with that because there is one thing which is very characteristic, is that this first attempt does much better in performance than all the other competitors, which are using programs developed by generations of researchers trying to analyze images. And the next year, 1 year after, at the competition, all the contenders arrive at the same kind of performance. They are all using neural networks. So it means two things. It means that neural networks are much better, and it also means that they are easy to work with, because all the teams in 1 year were able to switch from what they were doing to doing neural networks. And I think it's something one has to keep in mind. In the end, neural networks, the way it is done nowadays, it is something simple. It uses simple math, it uses simple tools, it uses big computers, for sure, but it's very simple. The second benchmark I want to mention is AlphaGo in 2015, and especially the version 0 in 2017. The version 0 is a moment in which they were able to train a neural network to play Go without using any historical recording of Go games. So it means that the software plays against itself, basically builds a competition of various aspects of the program and selects the best ones, and that wins. And it wins, and it starts to develop. I'm not a Go player, or I know the rules, but I'm not a good Go player. But people tell me that it starts to develop a way of playing Go, which was never seen before. And Go is a game that has been played by people for thousands of years, 3,000 years, 4,000 years. And so, but of course, it's a very, I mean, the number of combination is extremely large. And so it's not that surprising if you think about it, that a program that starts from scratch is able to explore new way of playing, which have never been seen. And aside, just a small aside comment, I think it will be the same very soon in mathematics. I'm pretty sure that we will, I mean, mathematicians, some mathematicians are starting to use AI in order to develop new way of doing mathematics. I'm pretty sure that there will be new directions of mathematics to be explored that we have never seen. Because basically, the human playing Go or doing math, we elaborate on what has been done just before us. And so we go one path and we add one increment, etc. It's very nice, but there are probably a completely new way of developing things. Okay. The big hit in science was AlphaFold in 2020. The ability to predict the folding of proteins starting from their sequence. It was a very challenging problem in which there was a lot of people working with heavy computer tools, molecular dynamics, etc., etc. And the purely statistical approach of AlphaFold was the one that won. And then in the last 3 years, the arrival of language model, which was also the same thing. I mean, an incredible performance if you think about it. Even if one can criticize a lot of what is coming out, still it's very spectacular that it's able to generate sentences which are syntactically and semantically correct and good. Of course, there were precursors. And the first precursor was the perceptron 1957. In 1957, it was supported, it was Rosenblatt. He built the perceptron. The perceptron was C+ neural network, one layer of input and one output, or I mean, direct layer of output connected to the input. It made the headline news. It was in the New York Times. It was supported by the army. And the argument was, with this machine will be able to think, to reproduce itself, to talk, to interact with the world. It will change the game. That was 58. So, and then a few years later, people realized that it's only able to make linear separation. And with that, you cannot do a computer, let's say. So, but of course, as soon as you add several layers, then you go beyond this criticism. And then there was the Hopfield model in 1983, the Boltzmann machine developed by Hinton in the 90s. And last year was a big celebration of AI with the Nobel Prize in chemistry given to the protein folding prediction, and the Nobel Prize in physics given to the precursors, to Hopfield and Hinton. The impact is absolutely major. I will not comment on that. One comment I want to say is that none of these breakthroughs that I mentioned only a few of them just to have landmarks, none of them was really anticipated at that level of performance, even by the experts. If you ask 5 years before, people say, yes, there is a statistical approach to language, etc. But thinking that all of a sudden it will put aside decades and decades of very specialized, very heavy, very good work on the structure of language and substitute it by a purely statistical approach is something that was not really anticipated. So in machine learning, whether it is, I will speak mainly about feed-forward network, which are the ones that are really the tools that are most used experimentally these years. And but it would also go for, if you look at the energy-based model, like variants of the Hopfield model. In all cases, you have, let's say you have a certain input, you want to, like it could be an image, you want to associate an output, and you have a neural network. And neural network is based on neurons. The neuron do something very simple. They do a weighted sum of the inputs of the other neurons. So if I look here, this neuron looks at all the signals coming from the neurons in the previous layer, put some weights on each of them, does a linear combination, puts a threshold, and passes this signal to the next layer. I mean, it's linear operation, it's a sum of weighted signals plus a threshold. hard to do something simpler than that. Of course, it means that what is a neural network? In order to design it, you have to decide how many layers there are, how many neurons there are in each layer, and above all, what are the weights? If I look at the signal received by this one, maybe it receives a strong signal by that one and a weak by this one. How do you choose them? And this is a challenge, and the challenge is really you have an input and an output, and you have a weight. The machine is completely deterministic. So if I know the weights, if I have trained a machine with some weights, you present an input, the output will be easily computed. You just pass the information through. It's even very fast. And what you do is that you learn the weights from a database. So you have a database with pairs of inputs and outputs, labeled images, so images in which you say that is a cat, that is a dog, that is a man, etc. And you have a database like that. And from this database, you want to learn the weight. And what has been done really is something very simple. You can do it with Bayesian learning, or you can do it with optimization. If I look at optimization, I would just say for each of the patterns in the database, I compute the output of the machine. I compare it to the output that I desire. I square that, so I have a quadratic loss, a quadratic energy, a quadratic penalty, and I want to minimize that. So I want to find the W that minimizes the error. Very simple. Or you could do it from a Bayesian point of view, and then you would have some prior on the weights, and then exponential minus beta times the energy or the error function, and you want to sample from that. These are two aspects of the... In all cases, what you have to understand is that you have a database, you want to find the weights. All this, I should have said it, but it is taking place in extremely large dimensions. That is, in modern LLM, for instance, the number of weights is in the range of tens of billions, hundreds of billions even. And so you want to optimize to find a solution W, which minimizes this function. It's a function in a 10 billion dimensional space. Looks like a small challenge. I mean, if you start playing with your computer, with your laptop in 5 dimensions, you get a headache if the function is not smooth, etc. So it's not convex, let's say. And so, and of course, because you have all these many parameters, you need very, very large database. So but now if you look at this expression here, this expression, it is a probability distribution in a very large dimensional space. They have these variables, which are the weights. They interact between themselves. And this is like an energy. And this energy, it depends, of course, on all the weights, but it depends also on some external parameters. And these external parameters, they are the database. So this is an example of what in statistical physics we call a disordered system. It's all this is the probability distribution for the W. It's a problem of statistical physics in which the interactions are governed by the data. And so the data are what in statistical physics of quench disorder we call the quench disorder, the external disorder. I give you a database. Given this database, you have to sample from this distribution. Another database, you have another sample. You train again this system. So this is a challenge. If you want to do theory, there is another challenge, because theory, it's not a good idea in general to do theory with one database. Because if you do theory with one database, it's okay the first week, but after a few months and years working with the same database, you start to have your theory, which is perfectly adapted to that database. But that's probably not what you want to do in theory. In theory, you want to understand the mechanism. You want to understand how the system, what are the generic mechanisms that make it such that a machine learning system learns, let's say. And can you apply it to a new problem with a new data, etc. So because of that, in statistical physics, we have been trained at designing ensembles. So ensembles of problems are like ensemble of samples. If I think of spin glasses, for instance, in spin glasses, you have interacting spin systems. And an ensemble is just to put the spin on a lattice and generate the interaction randomly between them. That is an ensemble. It was defined by Edwards and Anderson. And it's extremely important because then you can start to develop two things. You can start to see what are the properties that are not dependent on the sample, but which are just the property of a typical sample in the ensemble. That's what we call self-averageness. And then there are, of course, very specific questions, which is, given one realization of xi mu and y mu, how can you get the optimal W's, which is an algorithmic problem. So you separate the two. And this is what has been done in statistical physics. I mean, it happens that I still remember what happened in the end of the 80s and the beginning of the 90s, that there were a lot of statistical physicists working on a neural network theory because of all this, because it's a problem of statistical physics. But if I had to criticize what we did, and I put myself in all this group of people who are doing there, I think that we had one weak point, and the weak point was that we were always using ensemble, which were very simple, very elementary. Typically, if you look at all the works on the Hopfield model, or even on feed-forward two-layer perceptron, etc., they try to learn from data which is IID data. Each component is independent of all the other. So we lose one big aspect of the problem, which is the structure of the data. And if you want to develop a statistical physics approach to machine learning, which is realistic with what is happening now, you really have to develop new ensembles of random data, ensembles which are structured, which are not IID or just Gaussian or something, but they have a lot of structure. And so by structure, I mean, there are typical structures, which is the fact that, for instance, if you take images like MNIST database of handwritten digits, they are in MNIST, they are 784 pixels. So it's a point in 784 dimensions, each digit. But if you look at these points and you look at the distance between the points, and you look how the distance of the closest points depends on the number of points, you get an effective measure of the dimensionality. That's something that was well known for people doing strange attractors, for instance. That's how you measure the dimension of strange attractors. And if you measure the effective dimension of handwritten digits, you find that it is around 14 or 15. So it means that the handwritten digits, they are not random points in 784 dimensions. They are points on a manifold of dimension 15. It's a complicated manifold. It's folded, it's a bit fuzzy, etc. But this is what you have. And in this manifold, there are 10 submanifolds, one associated with the 0, with the 1, with the 2, etc. And that's typically what you want to separate. So this is one structure, hidden manifold, and that's very frequent in many databases. There is the aspect of composition and the combinatorial aspect, that if you look at an image like that, you have, of course, several characters. Each of them has a head. In the head, there are eyes, etc. You have various aspects at every scale, and it's a combinatorics of all that builds the image. There is a multimodality, and here another aspect which tells you that there is structure on very many scales. It is the spectrum of the correlation matrix. From here, it's from a database of text, and it is the distribution of eigenvalues. And you find that there is a power law distribution of eigenvalues. It tells you that there is structure on many scales taking place in this database. So all these are ingredients that you would like to take into account in a good ensemble of data that you want to treat with statistical physics. And that's one of my projects in the next years. And in order to address this question, I think that there is something which is very important, which is generative models. And so if I look back at what has happened in neural networks, I would say that nearly everything was there in the 90s, in the early 90s. We knew all of that. We had the training algorithm with the backpropagation of gradient. Everything was there. But there are two or three new things: the database, clean and large database, computing power, libraries that make it easy, much easier to program the thing. And then this allows to train much deeper network, numerous tricks that I don't enumerate here, and the generative model. Let me just, I like this plot because I think it's everybody should have this plot in the head. That is the size of the network, the size of the amount of training that you have to do to train the models that perform the state of the art at certain moment in time. And that is in petaflop per second days. And let me tell you that here, somewhere here, there is a number that I remember very well, which is 10 to the 23 floating point operation. So this is 1 mole of operation. So it's in log scale, and that's time. So you find that between the 1985 and 2012, you have a straight line. So it means that you basically the size of the amount of compute that you inject in the model in order to achieve state-of-the-art is doubling every 2 years. That's Moore's law. So that's not surprising. We have that in everything that has to do with computing. Starting in 2012, we can change completely the slope, and we are now at and this stops in 2022, but now it still follows. And so you find that this is AlphaGo 0, this is GPT-3. You find that the slope is much higher. It doubles every 4 months or something like that. So this is something that we have to keep in mind. And you see the announcement in the newspapers, etc., that OpenAI is raising tens of billions of dollars for next year. And that's for this. That's because they are following this law, basically. Okay, but so all of this is new. This is new just because it's more, we are much stronger, we have much stronger computing power. But the thing here is really new, and that's something that we did not have in the 90s. It is generative models, and I like it a lot because I think it's both amusing, interesting, very physical, and I also see it as a lens to understanding the structure of data. So what is generative model? Generative model, this is a toy example that I drew this summer. I was teaching in Molveno at a summer school, and I asked, could you generate an image with a group of theoretical physicists at a meeting in Molveno, writing equations on a blackboard in front of the lake and the mountains? And it generates that. And I'm sorry. It generates that. So if you know Molveno, you will recognize the lake. The lake really looks like that, beautiful lake. You maybe recognize the mountains, but if you're on the spot, you realize that the mountains, they are not there. They are actually backward there. So they should not be there. They are on the other angle. And there's a shore of the lake. Everything is nice. The theoretical physicists, they really look like theoretical physicists. Look at them. They don't look at each other. They look at the blackboard. They interact in a very strange way. But this is very realistic. And they are all men. I mean, there are all other aspects that I could elaborate upon. But so, okay. The equations on the board, some of them have decent aspects, let's say, but many are very strange. If you look at them, there are symbols that nobody has ever used in this audience and that do not exist probably. And so, okay, I think it's an interesting example. So that is what is generative diffusion doing. Generative diffusion, you give a prompt or something, it generates an image. And I think it's both fascinating that it is able to generate that, and very interesting to try to understand how it does it and what are the limitations. And so diffusion models are really the state of the art in image generation and video generation, and now getting to text generation also. So let me take some time to explain the principle, because the principle is totally physical. It's statistical physics of stochastic processes, really at its heart. So the idea is the following. There are 2 stages. There is a forward direction and a backward direction. So in the forward direction, you take data. So you have a database of images, let's say. For each image, you add noise gradually. You add noise and noise and noise until you have a pure noise. And then in the backward, you will train a system to denoise. So you will train a system to be able, when it has this image, to get one step of denoising, let's say. And so you will start from pure noise, you will generate pure noise, and you will gradually denoise until you get an image. And if things work well, you generate this image that I was showing to you. So let me go into the math. The system is relatively simple. Here I will look at yes sorry, no, it's okay. Yeah, Raffaella told me that I should do a little bit of introduction. So I have one slide of introduction on Langevin and Fokker-Planck, etc., so that people can really try to follow exactly how it connects, let's say, to the lectures that we have had at school on stochastic processes. So imagine that I have here one particle in a d-dimensional space, x. It's described by its position x of t. And it follows an evolution equation, which is, it has a time-dependent force. It's an overdamped equation. So the velocity follows the force plus some noise. And eta is a Langevin noise. So it's a Gaussian noise, which is delta correlated in time. Okay, so that's just Langevin equation. If you are uncomfortable with that, you just discretize it, and you say that you have a stochastic process in which the position of the particle at time tn plus 1 is the position at time tn plus epsilon, which is the difference of time times the force, the square root of 2 epsilon times the Gaussian random number. So this is very well defined. In the limit epsilon goes to 0, you get this Langevin process. And if you look at the probability distribution of the particle, so imagine that you start the particle at 0 at the origin, at time 0, and then you look at the probability distribution of the particle to be at x at time t, and it's very easy to find that it satisfies a differential equation, which is a Fokker-Planck equation. So the derivative of p with respect to time is the Laplacian of p, that is the diffusion. It's related to the existence of this noise, which is here. And then there is a term which is minus the divergence of f times p, and that would be the flow. If you had no diffusion, if you have no Langevin, you would find just a conservation equation, dp plus divergence of f times p is 0. It's just a conservation equation. But here you have added the diffusion due to the noise. Okay, so this is very standard. Let us apply that to our forward process. So the forward process is the following. Let me generate the standard initial distribution. I have some data, A, which is generated from some probability P0. Okay. Maybe I don't know what it is, but it exists. Let's say that it exists. I start from each data point and I noise it using a Langevin equation. And the one that I will show here, I mean, there are many variations, but it's all the same. So let me use the simplest one, which is called Ornstein-Uhlenbeck process. So it's dx dt equal minus x plus eta of t. So the force is a force that takes you back toward the origin. It's force minus x. But there is a noise. And so it's a linear force field. The linear force field means that the potential is quadratic. And the Fokker-Planck equation tells you that at large time, the equilibrium property, the equilibrium distribution is e to the minus the potential, so it will be a Gaussian. So if you let evolve a particle with this thing, at large time, its distribution will be purely Gaussian. You lose the memory of the initial condition, and you have a pure Gaussian. This is one trajectory. I start from this point here, I do it in one dimension, let's say, and the blue is one trajectory, and you see that there is at time t, the position of the particle. It is a e to the minus t. A is the initial condition. So e to the minus t would be the distribution that you have without the noise. And then there is a noise term. And the noise term is this thing here, which is a Gaussian noise. You just have to compute its variance, and you get this. So you get a mean trajectory, which is the exponential going to 0. On top of it, there is a noise, and the noise increases in time. The variance of the noise, initially it's very small, but when times increase, it goes to 1. So you get something which is purely Gaussian. Okay, so that's how you noise your database, and you do that for any image in n dimensions. Works the same. So if you start from, let's say, 2 Gaussians like that, you noise, you get a simple Gaussian. Now, the denoising, the backward process will be starting from large time, where you have generated the Gaussian distribution. You want to denoise. And how you do that? You do that by the following trick. Basically, let us look at the Fokker-Planck equation. And I just reverse the sign of time. So I want to go, I start now from large time, capital T is large here, and I use a time which is tau, which is capital T minus T. So that would be tau equals 0, that would be tau equal capital T. That's my backward process. Tau is the time of the backward process. Okay. I take my Fokker-Planck equation, I change T in capital T minus tau. What I do, the only thing I do is I change the sign of d tau. And so I get the Fokker-Planck equation with the minus sign instead of the plus sign that I had before. That's rigorous. Now, this whole trick is very easy. It is to realize that if you change the sign of the diffusion term in order to have a positive diffusion kernel, you have a positive Laplacian. Then you have to compensate because you had minus Laplacian, you turn it into plus Laplacian. In order to compensate that, you need to have a field, a force field, which is x plus twice the gradient of log pt. If you do that, this is an identity. So it is something very simple. And the theorem, which basically I have shown you the proof, let's say, the theorem tells you that if you guide your backward system with a force which is x plus twice gradient of log p, then at all time of the backward process, your probability distribution will be the same as in the forward process. It means that if you push from a purely Gaussian at long time, you push it here, at time 0, you will generate samples from P0. So this is, it seems to be magical because you say I am creating signal from noise. I start from pure noise and I create this signal. But there is nothing magical because the guiding force that you use at each time, it uses this score. And this score, it is a gradient of the log of P. It means that the log of PT. So it means that it knows quite a lot of the probability distribution itself towards which it is guiding. So there is nothing so impressive in that when you think about it. So everything is controlled by this score. And so you have to understand how to use this score, how you can define it. So here I want to explain you what are the various categories of score functions that one could use. Okay, imagine that I know perfectly the P0 of A. I am interested in generating equilibrium configurations of an Ising model in 2 dimensions at the critical point. Okay, I know what is a P0, and I could maybe generate. If I know the P0 a priori, I am able to compute the probability of x at time t because it's just the convolution of P0 by a Gaussian kernel. So this is something that I'm able to do in principle. There might be some computational problem, but at least theoretically I'm able to do. So this would be what I call the perfect score. If I do that, I compute it perfectly, I use that, I will generate samples from P0 at the end of my backward process. Okay. Something that we never do because in general we don't know the P0, or if we know the P0, we are not able to do this integral, etc., etc. But that would be the principle. Then there is something which is the way that it is used in practice is that you don't know the P0. I don't know the P0 of the cats or the lecture halls or whatever. What is that? What is the distribution of images of cats? It does not really exist well, but I have a lot of examples. So I substitute P0 by an empirical distribution, which is a database of examples. And so if I do that, it means my P0 becomes the sum of delta functions on each of the points of the database. And if I noise it, I get what? I get a superposition of Gaussian. I get a Gaussian centered around each of the database point, A nu times e to the minus t, because of the Ornstein-Uhlenbeck process, with the noise variance delta t. So my empirical distribution at time t will be a mixture of Gaussians centered on the data. I have to take the gradient of the log of that. That gives me the score. And then there is what people really do is none of the two first. They do a trained score. So what people do is that you have to find a S of x. This is a vector field in d dimension. And what they do is that they train a feed-forward neural network. This is the input space. This is the output space. You have all the weights in between, and you train them. And you train them how? You train them in such a way that the parameterized, so here it's a parameterized score. The theta are all the weights that are here. You want that the parameterized score is as close as possible to the true score. That's what you need. But you don't know the true score. So there is a trick which is just integration by parts of a Gaussian, which okay, I have not put it on the slides, but it's a very easy trick. You use this trick and you realize that minimizing the loss, which is here, minimizing this error here, amounts exactly to minimizing this quantity, which is here, which is the parameterized score evaluated at a point x mu of t, where x mu of t is just a noise trajectory starting from a mu. And you want to compare it to what would be the gradient of the log of the Gaussian, which is x mu minus a mu e to the minus t. And you want to minimize that. That is nice because this is something that you can do on the database. You just need a database of initial points and of trajectories starting from them. And from that, you have something that you can compute. And you have a loss function. It depends on the parameter. You can take the gradient, and that's okay. That's where you start to burn a lot of energy in order to do it, because you have to. Yes, it's big database. It's big neural networks. You have to do that at all times. For each time of the process of denoising, you need to generate the score. But you see, the principle is very easy. So I told you how do we generate fake data. In order to generate fake data, we should generate new data. And this is one of the main challenges that we have to face in this setup. So in general, we have a big danger, which is the danger of memorization. Why is it so? Well, if we had started from P0 empirical, okay, noise it and use the empirical score to denoise, then by the theorem that I've shown you of the reversal of time in the Fokker-Planck, after the backward process, I will generate something from P0, okay. It means that I will generate one of the samples. So I started from a database and I generate one image of my database. I mean, it's a completely useless procedure. Okay, but people don't do that. People use a trained score. The problem is that if the trained score trained by a neural network, if the neural network is very big and you train it very well, it will optimize. If it optimizes from this formula, which was here, it will generate the exact empirical score. It only has, I'm sorry, drink a bit. So the system has access only to the data. The best thing that it can do is feed the data. If it feeds the data, it reproduces the data. And so it means that the whole construction the whole construction, if you want to avoid memorization, the choice of the score function is crucial. And it should be non-optimal. It means that either your neural network is not very powerful, or you train it in a lousy way. Otherwise, at some point you will collapse. It means collapse. That is, you will generate data that you already have. So some of them, I did not forget what time I started. So do you know what time I started?
We were 20 minutes more than 20 minutes.
Perfect. So the kind of questions that we wanted to address are the following. What happens when data lives in large dimensions? What happens if you have phase transitions, for instance? If we have data in large dimension, we know that we can have data which has different phases. What happens? How does the diffusion process reconstruct the phase transition? There is a big question of memorization, which I have already mentioned now. And in general, I want to understand how the backward process reproduces the structure, reproduces me the lake of Molveno without exactly collapsing, without giving me a picture that already exists of the lake of Molveno, but something which has the flavor. And so this is where statistical physics come into the game, because I think that it's really very useful to study it with statistical physics, with the kind of methodology of statistical physics, in which we study simple examples, toy models, we want to understand mechanism, but then we need to do all the steps to see if these mechanisms are at work or not in real data. So that is a kind of general direction in which I want to go. And I want to explore several aspects of it. I will go relatively rapidly with the symmetry breaking. I want to mention it because I think it's a very natural question for statistical physicists, and but it's very simple. I mean, it could become much harder, but we looked at it in the simplest possible setup. And so, in the simplest possible setup, what we wanted to study is a system which has a ferromagnetic phase transition. And we look at the simplest of all of them, which is the Curie-Weiss model, in which basically AI, so which is my initial points, they are discrete spins, plus or minus 1. They interact by pairs with ferromagnetic interaction. And there is probably n and missing in the denominator here. And with the correct n here, we know that there is a ferromagnetic phase transition at beta equal 1. And so for beta larger than 1, this probability distribution, it has a weight on configuration which all either have magnetization plus m or minus m. And m satisfies m equal times beta m equation of unit field. So that's a very simple problem of statistical mechanics. Let us generate, so I generate spin configuration from this model. And this is where, and I plot their magnetization. And obviously, I did that with, I don't remember, a system of 4,000 spins. I find that the magnetization is basically either plus 80 or minus 0.80 here. I have two peaks of the magnetization. That is what I expect. I have my ferromagnetic system. And then for each of these, I start to noise I start to noise all this configuration. I do the forward process. And I look at the magnetization as function of time of the forward process. And what happens? Well, you remember the signal decays to 0 and there is noise added. And you see that there are all these trajectories. And in fact, if you look at large time, the statistics of the arrival point, you find a Gaussian of which 1 over square root of n, because it's a sum of independent bits. Sorry, they are not bits any longer, they are real numbers. Yeah, there is a small trick here, which we start from an initial space which is discrete, but as soon as we noise it, we go to r to the n. We start from a system of n Ising spins, which are on the corners of hypercube, but we noise it, we go to the inside of the hypercube. So here we see very well that there is a point where the trajectory starts to merge. And so there must be a process by which in the backward evolution, the trajectory will start to split. And so that is the thing that we wanted to study, and that's something we did with Giulio Biroli, and it's a very simple thing to do because the system is so simple. So you can write the score function explicitly, and you can show that using this score function, you look at the backward equation, and you find that the effective magnetization, which is here the sum of SI divided by square root of n, here in this notation, it satisfies an autonomous Langevin equation, single parameter. It closes on the magnetization itself with an effective potential. So that is the backward equation. And this effective potential, it's time dependent. And if you look at this effective potential, it has two limiting cases in which one it's easy to plot. If the time is long, that is the beginning of the backward process, it's just a quadratic potential. So you have an evolution of a particle in a quadratic way, just purely on Schneider-Bell. And then at some point, it starts to develop a cusp at the origin with two waves. And the height of the barrier between the two waves diverges with n, with the number of speeds. So it means that really, if you follow a trajectory in time, the particle will be here in this quadratic potential. It evolves with its noise, bounces back and there, okay. And then at some point, it starts to feel the double wave. If it has arrived by chance in the right-hand wave, it will stay there. And the two waves, they will become deeper and more separated. And you will develop them. So that is the moment at which you have this cusp is the moment at which you have the symmetry breaking. So there is a dynamical moment in the backward process at which the symmetry breaking takes place. You have dynamical phase transition. Exactly as you had in standard statistical physics, you had when you decrease temperature, you have a critical temperature where you start to have the two phases. This happens dynamically in the process. And if you look at it, it's of course, it has to be the moment that you expected from the images. That's the moment. So this is a very simple exercise that you can look on the back of an envelope to see what is happening with a simple model. Then we started to say, but do we have general criteria in more general data, which is not Curie-Weiss? I mean, Curie-Weiss does not interest much the people in machine learning. And so we realize that because this, what we call that phase transition, the speciation. It's the moment in which the trajectory starts to go in one species or another species. And this speciation really, if it takes place at large time, which is the case in all the data that we have analyzed, we can do an expansion in powers of e to the minus t. And it turns out to be exactly like a Landau type expansion. And so we look at the effective potential, the log of pt. We develop it to quadratic order, and we look at the curvature of this quadratic potential. When there is a one eigenvalue which starts to be negative, you have a phase transition, you have a symmetry break. And so this gives you a generic criterion, and you have to look at this matrix, which is the identity, minus e to the minus 2t over delta t times the correlation matrix of the data, of the initial data. This you can look at it from the database. I mean, just get an empirical estimate of the correlation matrix. You diagonalize it. When the time t, the first time t at which it has this guy has a negative eigenvalue, it's a symmetry break. So this gives us a spectral criterion that we have understood from a very simple model, but then we can test it on real data. And so this is an example of what I was saying, how to use statistical physics to study this kind of thing. And in order to test it on real data, we use a method that is the following. We start from a pure noise, run the standard algorithm up to time t1, and at time t1, we generate two exact identical clones of the image that we have gotten. And we evolve each of them with an independent noise. And then we look at the final time of the backward process, and we look if they are in the same species or not in the same species. So if T1 is close to the original time of the backward process, they go in completely different directions, so they will not be correlated. If T1 is towards the end of the process, well, with high probability, if you have a car here, you will have a car then. So you can look at the probability that they fall in the same category depending on T1. And this would be what you can compute it exactly with Gaussian mixtures, but then you can test it on the several types of database. This is a probability that the image generated by cloning at time T1, probability that they are in the same category, the same species. And that is as a function of T1, and it's plotted versus T1 over TS, and TS is a prediction that we have from our spectral criteria. And so they should all cross at the same point, and it's not so bad. I mean, it's a good first approximation what is happening for the speciation. So now I want to study the second aspect, which is this crucial aspect that I wanted to tell you, which is the memorization transition. And in the memorization transition, what we have is the following. So memorization is what happens if you have a very, very good, very well-trained neural network. And basically, it reproduces the empirical distribution. So what is the empirical distribution at time t? It's a superposition of Gaussian centered on each of the data points. And so if I start from time t equals 0, I have just delta points. So this is in the forward process. So this is my initial data. And I let t evolve, and the points move towards the origin. There is e to the minus t factor of Einstein-Uhlenbeck. And then there is a Gaussian cloud around each of them. And imagine that I started from A1 and I look at time t, my x is A1 e to the minus t plus a Gaussian cloud, plus a Gaussian noise, let's say. And if I start from this x and I go back, will I get back to A1 or will I get back to somebody else? If I am in this situation, you see that this x, it is very likely that it comes from A1. The probability that it comes from another guy is very, very small. And in fact, if you run it backward, it will go to A1. So it means that at this time, this is what I call a time which is less than the collapse time. This time is close enough to the origin of the forward process or the end of the backward process that the x is committed to going to one given data point A1. But if I go to further time, then the clouds become bigger, the points go closer to the origin, and everything is messed up. So the x starting from this guy, which is here, this x, I don't know in what cluster it belongs, so it's no longer committed. So from that, one can identify the setup and the moment at which there is a collapse. And technically, it's a very nice exercise in statistical physics of disordered systems. I will not develop it, but basically what you have to do is the following. Imagine that I start at time 0 from A1, I noise it, and I look at the empirical probability at x. And so I have one piece which is the probability which is due to A1 itself. Okay, this probability here. And I have to compute with the sum of the probabilities coming from all the other clusters. And there comes the beauty of statistical physics. I mean, in principle, all that is a mess. I mean, you cannot do much. But if you start to do that in large dimension, everything becomes simple. Everything becomes simple because this guy here, I know that this is just the noise. So the modular square of x minus a1 e to the minus t, it is the square of the noise, so it is equal to, in the good, it's a dimension of space, let's say. It's, either I call it n or d, it's called n. So the first term is just e to the minus n over 2, with high probability if you are in large range. What about the second term? Well, the second term, you realize that in order for it to be able to compete with the first term, you need to have an exponential number of points. And if you have an exponential number of points, you have a structure which is like a partition function with an exponential number of configuration in a space of dimension n. And this is what is called the random energy model, and which is the simplest model of disordered systems. So you can use the tools from a random energy model in order to compute that. And you balance the two terms and you find like that what is the collapse time. It turns out that after doing all this detour by random energy model, etc., playing like kids with the toys of the statistical physics, we realize that the final result it has an expression which is very simple in some sense. You just need to compute, you look at the probability distribution at time t, you compute its entropy, and you compare it to the sum of the entropies of n separated Gaussians, which do not overlap. When the two collapse to the same value, it means that you are just at the margin where, in this drawing that I was doing, all the Gaussian clouds, they pave the space reached by PT of x. So this is an entropy criterion. And the advantage of the entropy criterion, as it is given here, is that you can test it on any real data that you have. So we could do this test, and I will not go into the detail of this test, but it works very well. I mean, the entropy criterion gives you really the moment in which the thing collapses. So that is bad news, because it tells you that the collapse time takes place at, in order for it to take place at a finite time in the diffusion process, you need to have an exponential number of data. And I told you the images, typically they will go in a space of dimension, tens of thousands, maybe 1 million. You never have an exponential of 1 million. So what is happening in practice? What is happening? Like that. What is happening is that, first of all, the data, even if it lives in a space of dimension n, it actually lives in the subspace. The structure of data that I was saying before, you remember the MNIST, it was living in 784, but in fact, it was in a manifold dimension 15. And when you look at the same computation and you do it in dimension, effective dimension or an effective math dimension, then you find that the thing that matters is the dimension of the manifold. So n, the number of data that you need, it should be exponential in the dimension of the manifold, not in the dimension in which you embed the thing. So that's one first aspect. The second aspect is that in practice, people are not using the perfect empirical score, and there is regularization by the way that you train the neural network. And this is maybe, we have 4 minutes. This is maybe the last item I want to mention. It is just mentioning that if you have, if you really train a neural network in order to train the score, to get the score, this is what some experiments that we did on images. And on this experiment, this is a training time now. I'm looking at a database of images and training the score at a given noising time, let's say after time 0.1 of the diffusion process. I try to train the score. And I look at the quality of images that I generate with the training time now. I'm using gradient descent in order to train the thing. And I let the gradient descent evolve. And I see that if I train it well enough, after time of the order of 10 to the 5 iteration, this is a measure of the quality. The lower this number is called the FID. The lower this number, the better the quality of the image. After this training time, I get good quality. Now I look at the dashed line, and the dashed line tells me at what moment I memorize. It tells me what is the fraction of the images that I had in the database that I am reproducing by my generative process. And you see that it starts here. This is for a database of size 512. This is for a database of size 1024. This is 2048. So I reach a moment in which I have good quality, but then I start to memorize. And then you notice that the moment at which you start to memorize, it is displaced. If I have more data, it is pushed away. And that is the scaling that we have here. This is a memorization as function of tau, the training time divided by the size of the database. And so it tells you that if you have a large database, you have a large window in which you can train your system and get a good quality and not yet memorization. And so this is example. I mean, in all that you can show images and show that here you are memorizing. This is images generated at this time, and the first column is generated here. These are the images generated by the system, and these are the images of the database, let's say. And so you find that here it really memorizes as the curve is. shows it here. You can find the same thing by looking at the training error. You find that at some moment the training error, so it decreases initially with the training time. And then if you train very well, at some moment the training error really goes down. And the generalization shoots up. That is where you are memorizing. You are really having zero error on the training, but a bad performance on the generalization. And this time, it increases linearly with the size of the system. And so this is, yes, let me forget about that. This you can analyze also with a theoretical model, which is called a random feature model, in which you have a first layer of feature, which is frozen and fixed, a second layer of ways that you learn. And we could show by analyzing this, because the learned weights are only in the second layer, it turns out that the dynamics of training is related to the spectrum of this random matrix, which is here. This is a complicated random matrix, but we could analyze it using replica theory. And we found that the spectrum of eigenvalue, it has one big bulk, which is associated. Yeah, this is a big bulk, sorry. Seeing well from that, close to the screen. This is a big bulk. And these are eigenvectors or eigenvalues of order 1. It gives me a relaxation time of order 1. But then there is another set of eigenvalues which are very close to 0. If you zoom on it, there is a delta peak at 0, which comes from the rank of the matrix, and another bulk, which is due to the memorization. And you see they are very, very, very much separated. And their separation, we can show analytically that the small eigenvalue, they scale like 1 over the size of the system. So we get again this factor n. So basically, the lesson of all that is that in terms of the quality gets better and better and better until you get to a regime in which we call there is a generalization. And then at some point you have the memorization which starts to set up. And the separation of these two time scale is linear in the size of the data. So that explains how people have been, there is implicit regularization that has been used all the time when people are training the system. And because they train it with systems which are rather large, they easily fall in this intermediate regime. So this is just to give an idea of what one can do with statistical physics systems. And just to summarize, you look at the backward process. You start from pure noise. You have a first transition in which you start to have the speciation. Maybe you have a distribution with 2 clusters. So 2 clusters separate here. And then you have a second transition, which is a collapse in which the trajectories start to commit to one of the data points. And this second one, you can eliminate it if you train a neural network, but not too well. You have to train it in a window of training time, which is between the generalization and the memorization time. Okay, so you have to be a bit lousy. All this is done experimentally by people for many years, but it's typically very much uncontrolled. So it's trying to put a little bit of understanding to things which are, the case rather well known. And these are, thank my collaboration and some references. Okay, thank you very much. Sorry for being a bit.
We thank Marc for this very interesting talk. We have time for a few questions. I'm shouting so that they can hear us from the web. Adam, you can check if there are questions from the audience. But if there are from here, we can start from this audience. And a real experimentalist.
Experimentalist, yes, not as a statistical physicist. So it looks very much like data fitting at a certain point. You're finding weights. Okay, it looks like, but it's like data fitting of millions of parameters. So we know fitting experimental data is that sometimes the models and the data are so the models that you try to fit to the data are really correlated, and you will never find a solution. Instead, here, this works fantastically always. Does that have to do with this intrinsic dimension that you were mentioning, that it's much smaller than the number n of points. So the fact that really the training data are simple.
Well, I think that what you say is one aspect, but I think there is another aspect that I want to mention, which is really with AI and machine learning, statistics have started to enter in a new regime. And as we know from our physics training, if we have some data in physics and we feed it with 5 parameters, warning. I mean, maybe you are, but we are starting. And what AI has been doing is using billions of parameters. So we are in a totally new regime where there is a very strong possibility of overfitting. I mean, the number of parameters is very huge, but there is implicit regularization. And actually, the success of machine learning is due to the fact that these neural networks, these feed-forward neural networks that are the one that they use here to feed the score, etc. Although they have a lot of parameters, they have implicit regularization. That is, they are not implementing the most general function in n dimension. I mean, the most general function in n dimension, if I have a grid of 10 points in each, I have 10 to the n, I need to 10 to the n points. I never have that. So it means that they are not implementing an arbitrary thing, they are implementing something relatively smooth. And the task that you want to do is also, even if it is very complicated, it is relatively smooth with respect to this exponential complexity that you would have in principle. So that is certainly true if you want to separate cats from dogs, but it's also true if you want to generate a score function which is not too close to the data points, not too overfitting the data points themselves. So yes, there is this regime. It's a really new regime that we are forced to explore now.
Questions?
So thank you for this interesting talk. My question is about the diffusion and the role in this topic. And diffusion exists when there is a gradient of the concentration. For instance, if you have a drop of ink and you put it in water, there is a gradient in the concentration, right? And the diffusion exists, this gradient in the concentration exists. So the backward process in this topic, it seems to me that is creating this gradient. This kind of analogy could work for this kind of topic in terms of what happened, what could be the gradient in the concentration.
Well, I think that the score is basically plays this role of the gradient of the concentration that you are mentioning, and the whole process of training the neural network to get the score is to get the right gradient that will guide the diffusion in the right direction.
Any other questions online or? No, so far no. There are no questions online.
Thank you very much for the very interesting talk. My question is about the last things which we were explaining, that there's this time of order n where one can basically stop training and it works. Is this when the size of the model is fixed while one increases the amount of data, or is this in something like a proportional limit where both the size of the model and the size of the data set are increasing, that one has this separation of time n?
In the way we analyze it here, it was the ratio of the size of the number of data. The ratio of the number of data to the size of the model, which it's linear in this ratio.
Just
Sorry. Is it possible to do that by the diffusion model? If it is possible, or diffusion model.
Bayesian learning of the score, you mean?
Yes.
I don't know. I mean, I have not seen it, but there are many, many papers in this field that I haven't seen because it's a field in which there are many, many papers published every day. So I have not seen it. It's yeah, I was actually surprised that I have not seen it. So I would bet that it exists somewhere, but I have not seen it. It's not so clear. I mean, in some sense, using a Bayesian approach with respect to just minimizing the square loss. I mean, here it was minimizing the square difference between the score, the desired score, and the fitting score, the parameterized score, which is an obvious thing to do. Instead of that, you could use a Bayesian approach. This would be particularly useful if you have a good idea of what could be a prior for the score, which is not so easy to get. I mean, we start to develop a little bit of intuition of what the score should look like, but it's not our usual, you know, I think it's a very fascinating system actually that we're looking at, because simple aspects of statistical physics, you see them from another point of view. I showed you the phase transition. You have the phase transition in temperature, and you see that the diffusion, in some sense, the backward diffusion, the time it plays the role of a temperature. You start from pure noise, and at some time you start to see the structure in the specification. But it's not exactly the same thing. At high temperature, you would have an independent spin. At time zero, I have a Gaussian distribution. It's not the same. But at some point, you need to find the phase transition. I mean, you need to find the phases must appear somewhere. So you see that. So there are a lot of aspects like that that I think we have to educate ourselves to see how the statistical physics tells you how it goes. But, and I should have mentioned that, of course, people are also trying to use these ideas of diffusion in order to boost and to do some better sampling to help Monte Carlo methods in the regime where Monte Carlo. That's one obvious application they have no time to discuss.
So I think we can stop here. We thank Marc again for So next plenary colloquium on the Italian Society of Statistical Physics will take place in 2 months, and so we'll see the announcement on the web page of the society. So thank you to all of you. Thank you.
Thank you, Marc. Thank you, Raffaella.